the next lecture is by Pandey, and he'll be talking about conformal uniformization of domains bounded by quasitripods.
Thank you. Welcome everyone. Talk. First of all, I would like to thank the organizers for providing me this opportunity to speak here. Okay, so the title of my talk is just the title of the paper by Esmayli and Rajala, which is on the conformal uniformization of domains bounded by quasitripods. This is some kind of geometric condition on a domain, which implies that you have a uniformization. I will come to that part. What is conformization here? Okay, so classically, a uniformization means representing a surface or a domain by a canonical conformal model. Okay, so the first, like the term uniformization originates from the work of Pandey, where he proved the classical uniformization theorem that every simply connected Riemann surface is conformally equivalent to either this complex plane or the Riemann sphere. Okay, so basically the canonical model is either a Riemann sphere, complex plane, or unit disk. A conformal means you are deformed by a conformal to that canonical model. Okay, and in this talk we are going to focus on the conformal uniformization of domains in the Riemann sphere. Okay, so we have this classical Riemann mapping theorem, which says that every proper simply connected domain is conformally equivalent to the unit disk. And there are uniqueness conditions also, like either you normalize it by f of 0 equals to 0 and the derivative is positive real number, or you can say that the map is unique up to the post composition by a Mobius transformation of the unit disk. Okay. Now the question is, what if omega is not simply connected, and what should replace the unit disk as the uniformizing domain? Okay. Remember that we are always looking for a conformal map, but now omega is no more simply connected, and we don't know what should be at the place of unit disk. Okay. Okay, so for higher connectivity, there are several classical canonical forms. One is circle domains, circular slit disk, parallel slit domains, radial slit domains, etc. I will say something about the circle so that here. So a circular slit disk means we are to consider a circle. Okay, so we are taking a slits which are on the circular arc. Okay, so we are ignoring those slits. Okay. This is kind of a circular slit disk. Okay, and a point. And similarly, the parallel slit domain, radial slit domains, like with the name itself, it is clear. Okay, but we are interested in the circle domain uniformization. Well, I should mention that it is known that every domain in the Riemann sphere is conformally equivalent to slit domains. So that's not a problem. We are interested in the circle domain. That's the only thing which is open. So Kobe conjectured that every domain in the Riemann sphere is conformally equivalent to a circle. That is a domain whose boundary components are either points or circles. I will come to that point later. And he himself proved the conjecture for finitely connected. Okay. Okay, so this is an extra information. By a result of Sedner, we know that a domain is conformally equivalent to a circle domain if and only if it is quasi-conformally equivalent to a circle. Remember that this equivalence via conformal mapping and quasi-conformal mapping, that does not form the same class. Okay, they are different classes. But if our target is circle domain, they are equivalent. I mean, for example, two annulus are quasi-conformally equivalent, but they are conformally equivalent if and only if the radius has the proper moduli condition. Okay, so the main theme of the talk is conformal uniformization by circle domains. Okay, so since this conjecture is still open, and I will come to the point, I will come to the place like what are the developments on the Kobe conjecture. The natural setting is now to put a condition on a domain some kind of general condition, geometric condition or domain, and check whether under that condition it satisfies the Kobe conjecture or not. Okay, I will come to that point later. Okay, so this is circle domain. Circle domain, it can be very weird also. Okay? So you can have circles converging to a point, point converging to a circle, point components making a Cantor set, and the Cantor set can have the positive area also. These are kind of some kind of typical examples of Cantor sets. And the circle domains. This is just some food for thought. How bad a circle domain can get. Okay, so note that these circular boundary components can be at most countable because of the separable property. We have a countable dense set, so they can only be countably many circular boundary components. But whereas the point components may form a very large set, for instance, the positive area Cantor set can be on the boundary. But here is some question. One can think about it in their own free time. So the first question is whether the point components can be covered by countably many Cantor sets plus countably many points. It seems kind of that natural that okay, whatever circle domain you have, might be the case that the point components can always be covered by the countable many Cantor sets and countably many points. Okay, and can this be with zero area? Okay. And the other question is,
Sorry, what do you mean zero area?
I mean, the area of the boundary.
If it's
By
zero,
zero,
then
percent not positive area.
No, but you have Cantor set of positive area also.
It's not only three.
I mean, my question is that can this be done with the zero area?
All the countably many points.
Yeah.
like composites are the area are responsible for the area, and the other stuff is.
Oh, I see.
No,
So,
So they countable many points of zero area.
sorry.
Countably many points of zero area.
So what's the?
No, I'm saying that countably many Cantor sets. Cantor set itself is uncountable, and it can have measure area positive. Okay, so the question is, you take the collection of all point components, whether it can always be written as the union of Cantor sets, where this union is countable, plus just countable union of some points.
And what is the next question? Can this be done with the zero area?
So, like, find an example where this is not true. Okay, find an example where this is not true. Like, suppose if you are able to find such example where this is not possible, like the point, can that have zero area?
Oh, if that's not true.
Yeah, if that's it. So, okay.
Instead of countable, can you have zero area?
Yeah, exactly.
Oh, I see.
For the non-counter sets, yes.
So counter sets union is zero
Yeah.
measure set.
Suppose you have, yeah,
So instead of that union of PIs, you just add that zero measure set.
yeah.
But the counter set for you has a positive measure or zero measure.
I mean, it depends what Cantor set you take. I mean, it is up to
You
you.
consider anyone.
Yeah, I mean, you just give me an example where this fails, and then I will ask whether it has a measure zero or not. That's so. Okay, and the next question is, does there has to be any boundary point which is isolated from circle?
This is like, is this the perfect set property basically? Or?
It is. So basically, the theorem which we will be proving is basically that the union of closed, totally disconnected set cannot cover all the point components. I mean, that's a kind of bare category argument and some stuff one needs to do, but this is just some food for thought that you can enjoy and come up with some strange circle domains. Okay, anyway. Okay, so this is the development of Kobe conjecture. So simply connected was of course by Riemann, and as I said, that contains the uniqueness statement. Finitely connected is by Kobe, and that also has a uniqueness statement. So uniqueness, so whenever I'm talking about circle domain uniformization, by uniqueness I mean the same thing, that it is unique up to the post composition of the Mobius transform is Okay. Okay, fine. But remember that in the plane, for the unit disk, we have this very nice theorem which says that every conformal self-map of the unit disk has to be Mobius transformation. But that's not true for circle domain. So.
Sorry, can I ask a question? What is it about? There is complete and grown hyperbolic domains, right?
Yes,
En
yes.
deze grown hyperbolic is automatically complete, no?
Chrome hyperbolic, no.
Can you give
Like,
for example?
So any simply connected domain is Chrome hyperbolic, but you take the outward cusp, that's not fact.
Oh. Yes, sorry.
Yeah.
Thank you.
So of course, like one can ask that Chrome hyperbolic with respect to which metric, hyperbolic or quasi-hyperbolic, but that's a result by Heron and Buckley that it doesn't matter. Like they are simultaneously Chrome hyperbolics. That's fine. But for the Chrome hyperbolic domain, so these are some recent papers by Carafilli and Talampekos in 2025. They prove that every Chrome hyperbolic domain satisfies Kobe conjecture. Okay, the point was where I was. Yeah. So for countably connected domains, E and Schramm, Schramm proved it for countably connected domains, and it also includes the uniqueness statement. And for uniform domain, it is a result by Heron and Koskela, but in the paper, the uniqueness statement is not there. Yeah.
Can you maybe remind what uniform means?
Okay, so uniform means one is that quasi-convexity condition. It means that any 2 points can be joined by a curve. So that the length of the curve is less than equals to some uniform constant into the distance of those 2 points. Any 2 points can be joined by a curve. And this A is uniform, it doesn't depend on the point.
So that's just quasi-convex.
So this is quasi-convex, one such condition. And the second condition is known as the cone arc property. Like, yeah, so like you can join any 2 points, X and Y, which has on this cone arc property. You don't need to go too close to the boundary. Okay, sorry. This is my notation for a curve. Or L means the length of the curve. Euclidean length of the curve. Okay, so that's for uniform domains. It is by uniqueness is by Talampekos and UNC. And okay, so Schramm did it for the cofactor domains, the uniformization problem, but there exists a cofactor domain with positive area can intersect on the boundary, so that the uniqueness will. In fact, uniqueness is related to the rigidity problem, whether circle domain is rigid or not. Okay, so that's a known fact that if the boundary has positive area, the circle domain cannot be rigid. Okay, and the co-spread uniformization, which I'm going to talk about, is by Esmayli and Rajala, and they're also uniqueness fields. And Chrome hyperbolic domains, of course.
Wait, I'm sorry, can I ask?
Yeah.
So for co-fact and co-spread, the uniqueness is false, not.
Yeah. I mean, in general, there is no uniqueness statement for the Kobe conjecture.
Yeah.
Because it fails in the uncountably connected set.
So what's co-spread?
I will come to that point. I mean, that's the topic of it. Okay. But there is one important thing about the Kobe conjecture, which is the strong form of Kobe's conjecture, and which we usually want our map to behave like that. Okay. So you consider a domain in the Riemann sphere and consider complementary components and divide it into two parts, point components and non-point components. Okay. Now define equivalence relation on the sphere, which is defined by x is equivalent to y if either x is equals to y that belongs to the domain G or they belongs to the same complementary component. Okay, so that's an equivalence relation. and equip it with the cosine topology, you have a cosine space, and you have the projection map.
It's the same like all the.
Yeah, exactly.
Yes,
I mean,
yes.
so I will call this G as a domain and this part as a decomposition space. So whenever I'm saying decomposition space, assume that it is Z hat. Okay, so by Moore's theorem, this is homeomorphic to the Riemann sphere. Okay. And hence, if you have any homeomorphism between domains, it extends to a homeomorphism to the decomposition space. So the idea of the decomposition space is that you collapse every complementary component to a point in a decomposition space. Okay, so that becomes a point. Every complementary component becomes a point, and then you can like.
Wait, how is it homomorphic to the unit sphere if it's not simply connected?
It is simply connected because it is homomorphic. I mean, that's the Moore's theorem. So Moore's theorem says that whenever you have a nice equivalence relation on a sphere, the quotient by that equivalence relation is going to homomorphic to the sphere. And that nice equivalence relation means, I think it is basically about not every 2 points are equivalent. And this is one such condition. Second condition is, I guess, maybe I'm forgetting the other condition.
Okay, G hat is
Yeah. So like it's isolated.
When they converge to something, like it's like upper symmetry.
Okay, yeah, upper semi-conductivity of it. Any question on this? So the strong covariant conclusion is, okay, we want a conformal homomorphism to circle domain. That's fine. Find a map, conformal map. But we want that map so that the extension sends non-complementary components to the non-complementary components. Sorry, non-point complementary components of the domain to the non-point complementary components of the circle domain, and the point components goes to the point components. Okay.
Wait, this is confusing. So you can always take a point from the non-point, and I don't understand. You can just like remove points from the non-point
No, that
how do you define the point components and non-point components?
Point components means the diameter of the complementary component is 0. Non-point means diameter is positive.
Oh, okay, yeah.
Okay. So it is like for the, as I said in the circle domain. So see, this is non-point complementary component. These are point components. So this is what we want. And in the random examples, we have seen that this is not always the case. Even in the countably connected case. In the countably connected case, he and Schramm gave the conformal uniformization, but that conformal uniformization may fail to satisfy this. There are several results, but some recent results are there by Esmayli and Rajala, and I think also Lee and Rajala in their paper also. Some kind of examples are there where point components goes to the non-point components, and non-point component goes to the point. Okay, I already said this. Okay, so therefore, any question? Yeah.
Sorry, just to go for this is strong.
A strong covariant conclusion in that I want that non-points goes to non-points, point goes to point.
Yes, okay.
Extend the C case here. I will come to that point later, like what Schramm was doing and why that would not work in the Esmayli setting. Okay, so Schramm's compact uniformization, it all started with this one. Okay, so a compact set, this has already been introduced, so I will not pay much time here. So a compact set is called tau fat if basically the area of that set intersection with the ball is greater than or equals to tau r squared. And a domain is called co-fat if every compact complementary component is basically tau fat. Okay. Yeah, if people are familiar with the metric measure setting, this fatness is essentially opposed to regularity. Okay, because for domains, upper bound is always there. We only need the lower bound, and it says the lower bound. There's one more thing. Observe that point components are packed vectors. And non-trivial complementary component must have positive area at all relevant scale. What does it mean? It means that if your domain has a slit, that's not fact. Okay. If your domain has that example, that if a domain if a domain has outward pointing cusp, that is also not fact, because at that point you cannot have the area comparable to R square. Okay, so the Strand theorem says that every co-fact domain is conformally equivalent to circle domain with strong Fourier conclusion. Okay, so it means that in a co-fact domain setting, non-point goes to non-point, point goes to. Okay. And the proof, okay. So Strand introduced trans-boundary modulus in his framework on co-fact domains uniformization. And so, of course, it has been introduced earlier also. It allows curves to interact with complementary components of the domain. And this is kind of a central tool in later uniformization rigidity problem. And the paper, which I'm going to talk about, basically also relies on this framework. Okay. So this is the definition which you saw in the title, quasitripods. So we have a standard quasitripod. We have a standard tripod, which is just the union of these segments. We say that a set is quasitripod if it is a weakly edge quasisymmetric image of the standard tripod. Okay. Quasisymmetric map means whenever you have this, you should have this. So if the distance if x minus a is less than or equals to x minus b, the image should also satisfy with a uniform constant edge. This is known as a weak quasisymmetry. Okay. Okay, fine. What is the main theorem in the paper? It says that if we have a domain containing infinity, and suppose that there are two constants h and n, the first condition is the branching condition. The first condition is the branching condition, which says that every, also that we have I'm putting this condition on the non-point complementary components. So every non-point complementary components contains a quasi-tripod, which is comparable from the below to the diameter of that point. Okay. And the second condition is the packing condition. It says that the cardinality of all those non-point complementary components which have this diameter greater than r has to be always less than or equals to some constant n, which is uniform. Okay, I will come. Okay, I can create a picture how these domains looks like. So, just for visualization, this would look like something like either you have a solid quasi-tripod, okay, or you have point components converging to point, which make a quasi-tripod.
So the points are connected to the center.
Yeah.
So it's not just defined the joining points. It's
Yeah.
the center
Accumulated.
of accumulation.
Yeah.
Okay.
Yeah. I mean, okay. So it means that every non-point complementary components contains a large quasi-tripod. Large means it should have this one, and at every location and scale there are at most n large point components.
So just to explain further, I mean, in your picture, the first condition is that we cannot have one of these branches much larger than the tripod part, for instance, right?
Exactly. Yeah.
Yeah.
I always, yeah. That's the main point here.
And then the second condition means that you can not have too many tripods
Yeah.
or components in the same disk, which are kind of large.
Yeah.
What was the meaning of the first? condition.
Right, you cannot have a picture where you have like a pitchfork and like
Yeah.
snakes and then move like,
I mean, it cannot be like,
yeah, like that, you know.
they has to be comparable. The diameter of that complementary. Okay,
Um,
there's one observation, this I just wrote for the. But I will just skip it, which says that once you have the packing condition, this second condition implies that the non-point complementary components has to be countable. Okay, so in a domain which satisfies these two conditions, the non-point complementary component, they are always counted. Okay, and then Esmayli introduced the co-spread domains, okay, which is nothing but the local version of this condition one, this branching condition. And they in fact proved that this local condition implies the packing condition also. So that's another theorem in the paper. So a compact set is H spread if for every Z in that compact set intersection with C, and you take every R in the diameter of that set less than the diameter of that set, then there is an H quasi-tripod contained in the A intersection with that ball of that radius, with diameter T greater than R by H. Okay. And again, as same like it is said, co-spread if every non-point complementary component is S. Okay. And as I mentioned earlier, that this is a local version, of course, it is by the definition itself that it's a local version because you are taking the balls, for every point you're taking the balls less than the diameter, and so that you're taking the intersection of that ball with the set. That contains the positive ball. Okay, and the theorem is if omega is a co-spread domain, then it satisfies condition 1 and 2 with constants depending only on H. It means that once you have the local condition of this branching condition, it will imply the branching condition as well as the packing condition. That's the theorem of the paper. So consequently, co-spread domains admits conformal maps onto circular domains with a strong Overbeck conclusion. Okay, let us see some examples and non-examples of co-fed versus co-spread domains. So if you want to see a geometric nature, the co-fed domain says that the complementary components are area thick, okay, because they contains always the part of the area. And the co-spread domain says that the branching of complementary components at all locations and all scales. I mean, you have the branches at every location, every scale. And the local condition is that the area is comparable to R square, and in the co-fed, in the co-spread, it contains a quasitron. Okay, non-point components, it must have a positive area, okay, because that comes from the definition itself. And in the co-spread domains, it can have zero area. Okay, so that's the kind of, it is, for me, it is important to mention that what are the differences between co-fed domains and co-spread domains, because in the Schramm proof, this condition basically gives a very, very beautiful condition on the diameter of the complementary components. That's basically an L2 estimate. I will come to that point. And that is very crucial in the transboundary modulus estimate.
May I ask a question? So, co-fed and co-spread is there any relation between those? And can we say like something?
No.
No.
Okay.
So something can be really like it can be very very spread, but not fed. Yes.
Yeah.
So something like this.
Yeah.
I can't come up with example that is like really fed but not spread. Can you help me to that?
I mean, which is fed but not spread.
Yes.
Okay, so
I think it can be something like this.
It's not.
I mean, you can take the domain. You just remove the Cantor set of positive area from the domain. Fed components, point components are fed vacuously.
Okay.
And so, but that's not co-spread. Well.
Okay, what will like simply connect it?
Well, wait a minute, so that's area is 0. Yeah, area is 0, that's not cofat. You take a counter set, remove the
But
counter
if
set.
you can remove
Area is 0.
multiple number of points and make it non-spread but cover but fat. But
Making cofat, making a domain which is not a cofat is kind of simple, like you just.
yeah, it's simple. I'm asking the opposite question, something that is fat but not spread.
Or something that is fat but not spread.
And
Yeah,
for
so you take a counter set of positive area, but that can be spread.
I think Jensen said to me today that it's like you take some sort of spiral tension. That's a question to you, I think. What's an example of a cofat domain which not called close spread?
yes, spiral works.
Yes, it just like a spiral, because their condition in Esmayli Rajala's paper is that they have quasitripods and the packing condition, but if we can construct a spiral like maybe I can draw.
Yeah,
sure.
spiral work. Bauman. Population.
Yes.
That's rather honest.
And just like this, so you can think that when this get tight, and then it cannot support quasitripods inside. So it's not, of course, it's not cost-bearer, but we can prove that for every point we can find the cofatness is, this is a fat site.
Okay, thank you.
Why is it not spread?
Because
If we had the tripod with the point, like with the limiting at the center.
I mean, just by the
Because
geometry
it's
picture,
not branch, you have that.
Yeah.
You don't have to.
it's kind of branching is not there.
because
And why can't we just choose like closer and closer points to form a? I mean-
because actually the cofatness is an area condition.
Yeah,
And the quasitripods is that you need
Branching
to
condition.
find 4 points that make as a stable structure. It cannot be like this.
I mean, of course, in this picture, you need to write down the estimate so that this is not co-spread. Otherwise, just a spiral, I'm saying that it's not co-spread. Work. There will be some estimate.
Actually, this is not the line, you can think as a strip, but the strip gets thinner and thinner when you just throw to the original points. And then it means that it's a very thin spiral. And when you just let this to be the complementary components, then because the inside is very, very narrow, so you cannot always find the quasitripods inside.
Oh, are we talking about the spiral of the complement?
Yeah, complement of this.
Yes, complementary.
Complement of this.
Actually, it's just a spherical domain or a flat domain.
And
This is
kind of you need to shrink it something like this. So that it will not be co-spread.
Thanks a lot.
Anyway, so non-examples we have already seen the cofat domains and co-spread domains are like slit or arc component you can state. And they both are quasi-Mobius invariant. So in particular, they are quasi-conformally and hence Mobius invariant. Okay. Now we'll move towards the proof of the main theorem. Okay, so it requires the transboundary modulus estimate, but very different from the what Schramm did. So in the Schramm cofat theorem, fatness converts diameter into the area, okay, which is nothing but ultimately going to give us this diameter, L2 estimate of this diameter. Okay? And this is quite useful in the transboundary modulus argument. But of course, this we cannot do in our setting, in the co-spread setting, because the complementary components can have zero area. Okay. So that area thickness is not there. So unlike cofatness, the condition in Esmayli-Rajala's theorem do not imply L2 control. For example, like as I said, it can have zero area. And one such example is Julia set of z square plus I. Therefore, the proof of theorem 1.3 needs more delicate transboundary modulus estimate. And now I'm going to talk about what is transboundary modulus. So it has been introduced earlier also, so I will not put much time on it. So it is just, we put an area measure on the decomposition space, which is just the limit measure on the domain and the counting measure on the complementary components. And then you define a metric, an extended metric on the decomposition space, which is a Borel function, and its area is defined by rho squared over G, and just take the value at these complementary components and the sum. Okay, and the transboundary length of the curve is nothing but you take a curve which in the decomposition space, so it means it's just a continuous function, and you take a pre-image that has countably many components, and on each component you take the part of the curve gamma then restricted to that component, and there we can talk about the classical length of the classical line integral of the curve. Okay, so that's just this one, and which can also be written as in this form. So this is well defined. In particular, it is infinity if some of these alpha j's are not locally rectifiable. Okay, and the transboundary length is nothing but the length of the curve in the domain part, and other is summed at the complementary components. So this is the transboundary length of the curve, and we say that a family of paths in the decomposition space. Okay, so if we have a family of paths in the decomposition space, and we say that a metric, an extended metric is admissible if the length is greater than or equal to 1 for every curve in that family. And we define the transboundary modulus as the infimum over the area, I mean the transboundary area of that. Transboundary area of that metric, extended metric. And the basic properties of transboundary modulus are conformal invariance and other properties of usual modulus, which implies the sigma algebra properties, subadditivity and monotonicity and all. Okay, now the proof of theorem 1.3 depends upon this theorem, which says that if we have a finitely connected domain satisfying condition 1 and 2 of theorem 1.3, then there exists a uniform constant m, which depends upon h and n, which are there in the theorem condition 1 and 2. Then the transboundary modulus of the family of curves is always bounded by f. What are these family of curves? These are family of curves in this annulus. So, okay, whenever we're denoting pi of omega, is just because of the preciseness, since I'm dealing in the decomposition space. So that's why I'm denoting it pi of omega. But in your mind, you just picturize it as so this is an annulus with outer radius 2r and inner radius r, and joining circle of, okay, wait a minute. It should be outer radius 4r and inner radius r by 2. Yeah, 4r and r by 2, and joining the circles, the complement, the boundary of this annulus. So this is the main part of the paper, okay, and the proof of like this is kind of technical core of the paper, and the proof of this is really technical. But I choose another way. So here I have two ways: either try to prove this theorem, or to show that how this theorem implies the main theorem. I'm going to do the second one. So we are going to discuss how theorem 3.1 can be applied to prove theorem.
Before you continue, can you maybe draw the estimate for the
Yes. So okay. Okay, so first of all, observe that here I have written the finitely connected thing. I will come to that one later. Why finitely connected? So if you have a domain which is finitely connected, okay. Now it says that there exists some constant m, so that the modulus has the finite upper bound, and the modulus is basically take this complementary component a, let us say a, and and take the circle surrounding it. Which is maybe 4R and R by 2, and then you want, of course, this part can also have complementary components. Okay, like, since it is finite, we can also assume that it doesn't have, but it can have this complementary components also. So the transboundary modulus of this curve family is always has this finite upper bound. I will come to this picture later.
I mean, it's like a very important point that what he considers A can be a complementary component, and complementary component can intersect both inner and outer circles. So that's like an important thing, because if it's about if it doesn't intersect,
Right away.
right? So I'm like,
I,
if it's like,
I took the point complementary component.
yeah, if you take like a big one.
Okay,
Like that, right? And then you
Yeah.
look into the curves.
so that if we have these kind of curves,
Mhm.
then that would, those are the main things, since it is touching the complementary components.
And usually these kind of things which are, they act as bridges between inner component and
And
outer component. They usually increase the volume.
Exactly.
So the fact that you have few of them is the reason you have that
Yeah.
cracking condition, is the reason that you have things. And the fact that you have tripods is because if you put lots of splits going like that,
Yeah.
that would increase your transboundary
Ah.
modulus a lot.
Yeah, I mean, okay, yes. Thanks for that point. Yeah. Okay. But as we see, as we have seen that by the packing condition, we can always assume that this is countable. So, and for k equals to 0, we define a finitely connected domains. Okay. Where removing these complementary components, and we can always assume that these are non-point complementary components. Okay. These are non-point complementary components. So by Covey's theorem, these finitely connected domains has conformal map to the circuit domains, so that these map GK extends to the decomposition space of this one and this one. Okay. And for every natural number, this subsequence of this one has a further subsequence which converges in the Hausdorff topology. And so it is either a disk, I mean, disk, by disk I mean this, and deleting the circle domain. So disk I mean the circular part of the component, and or just a point. And then since we have every subsequence has a further subsequence which converges in the Hausdorff topology, we can find a diagonal subsequence so that this GKJ converges locally uniformly to some function f. Okay. And I will denote this GKJ by just Fj. Since we have now this subsequence, these domains will be denoted by just omega j, and these circle domains will be denoted by Tj. Now the question is, what can get wrong in this limit? Okay.
Can we go back just for a minute? I'm just trying to catch up.
Okay, I think I can explain again. So we are constructing
Very fast, just explain again.
Okay, so since by the packing condition the non-point complementary components are countable, just enumerate them and consider finitely connected domains. Now all these finitely connected domains has conformal map to the circle domain. Okay, and you take the extension to the decomposition space and define this thing. So it is either a disk, I mean, since this is finitely connected, this has to be disk. Now all this sequence, now I will take this k, I will run this k, since k is greater than or equal to 0, I will run this k, and now this subsequence of this one has a further subsequence which converges in the Hausdorff topology to either a limit disk or a point. And the limiting thing is either a disk or a point. And then by extracting a diagonal subsequence argument, I can assume that these maps G, K, J, okay, they converges locally uniform with some conformal FF. Okay. Now, what can go wrong in the limit? So, either, first of all, we do not yet know whether the image of omega under this limiting map F is a circle domain or not. For that, we need two things. These point components goes to, okay, so this can fill in two things. Either this point components neither a point nor a closed roundness, or this non-point complementary component goes to some point component. Okay, I mean the diameter is 0. Okay, so since we also need the strong Covey conclusion, we must also rule out the possibility that non-point complementary component collapses to a point. Okay, so there are three things we need to do. First one is that points should not go to non-point, and the second thing is, so this is the first thing, point should always go to the point component, and this non-point complementary component always correspond to this QL, which is either a point or a disk. This QL is the limiting thing, which is always a point or a
And
disk.
then we should show that it is a disk.
Yeah, and then it is a like it is always positive. The diameter is always positive. Since this QL is always a point or disk, and if you show that diameter is positive, it's a disk. So the point is to prove 2, 3, and 4, and this is going to play the role in proving 2, 3, and 4. Okay, so this is the now step 3. We need to consider relevant path families. So the first thing is that take any complementary component of this omega and take a Jordan curve separating from the rest. Now, okay, let us say this is the complementary component, and we can always have points converging to it in the domain omega. Okay. For each m, take what is it? Okay, so J is some Jordan curve. And with Bm, we take a segment connecting this complementary component A and this Bm. And we are now going to construct two path families. One is that join this thing with this J, or the other thing is that this wedge J is basically path separating J from P. Oh yeah, so the path of this one, these families of curve, and the other one is kind of.
That segment should be very small, it should be inside the Jordan curve.
Yeah, I mean, this BM, I will take M sufficiently large so that.
Yeah, so it should be very close to your.
Yeah, I mean, these are, BM are basically, okay.
And the way you drew it, the curve is.
Okay, well, I'm all, okay, because my proof, because the thing is that I'm going to use this gamma J for the proof of 2, so there I'm going to assume that this is just a point. Okay, and I'm taking a sequence BM converging to this point. So basically, of course, yeah, this should be this BMs, M should be sufficiently large so that this is in J. Okay, now the idea is, idea for taking these two curves are basically this gamma J is to prove 2 and this is to prove 3 and 4. Okay. Now this is the main thing. These families are chosen so that theorem 3.1 gives the required upper bounds. So using theorem 3.1, we get a upper bound that goes to 0 on these curve families, gamma J. Okay, just remember this one, equation number 5. the transboundary modulus is always less than or equal to this function, which goes to 0 as r tends to 0. So ultimately, in my for the proof of 2, my r will be this one. Okay. And for this curve family, theorem 3.1 gives, I mean, of course, it is not easy that, I mean, it is not easy to see that theorem 3.1 gives this one, but of course, that's a proof, but it gives a finite upper bound. Okay. How we are going to use this 5 and 6? With, of course, with the circle domain estimates. So this is also established in the paper that once we have this conformal map from omega z to dz, where each dz is a circle domain, there is a homeomorphism depends upon this complementary component. So if the lim sup of the family of curves in dj is greater than or equal to lim sup of the image of the distance between fj of this complementary component to the fj of this of the complementary component b bar. Sorry, b is not a complementary component. B is the points which are converging to this one. Sorry, B is not a complementary component. B is the points which are converging to this one. And if diameter again, so this thing will be used for this thing will be used. This thing will be used to prove 2, and this one will be used to prove 3 and 4. So proof of 2. Suppose towards a contradiction that a point component goes to a non-point complementary component. Okay. So of course we have these points in BM which is converging to A, and then the distance is always positive. Lim sup of the distance between Fj of BM and Fj tilde of P is greater than or equal to C for every M. Now the circle domain estimates gives that this modulus is dominated by this one, and this is dominated by phi p of C. So that you can just take the C naught as phi p of C. So this is always have some fixed lower bound, this modulus. On the other hand, theorem 3.1, if you apply theorem 3.1 with r equals to bm minus a, what does it give? It gives us that this transboundary modulus is less than or equals to theta of a of modulus of bm minus a. Remember that, I think you guys have noticed it, this curve family gamma j, although I have written only j, but it depends upon m. Okay, for each m it is like this gamma j depends. And then by the conformal invariance of the transboundary modulus, this should be equal, and lim sup of this one is less than or equal to this one, and this goes to 0. So choose m large enough so that this quantity is less than C naught, and this gives something impossible, and which is a contradiction. Any doubt here? Or okay, so I will finish it. This is a proof of 2, and then proof of 3 again goes back to the circle domain estimate and theorem 3.1. Now we will use the second part of the circle domain estimate, this one. So this is always infinity, but this gives the finite upper bound on the modulus. So that's again a contradiction in the third part. So yeah, I mean, so point components goes to point components and non-point goes to non-point complementary components, and we always know that either has to be disk or point. We have the conformal uniformization of co-spread domains, which satisfies the strong Pobet conclusion. Thank you.
Are there any questions? Well, I have a small question because in the Robinson parts, the Esmayli Rajala use the notation phi p hat. So why this is depends on p, or why it's this notation?
That notation was in the paper, so I just copied the same notation. But This statement is for each complementary component. So this homeomorphism has to depend, I mean,
So you mean for different complementary components?
there may be different homeomorphism. I mean,
Yes, I think this is the rough understanding, but maybe I checked last week, this is not the.
okay, so you are saying that for any complementary components, this will work, same homeomorphism work?
Because maybe it can, for the revision of our my paper is Rajala, so it's, this homomorphism can be written directly to be free, because it's not highly good, depends on the choosing of complementary components, if I remember.
Okay, I mean, that I don't know.
Because last time I asked the guy, he also don't know why he like this notation.
Yeah, I mean, in the paper it is written as phi of P, so I thought
Yes.
it depends upon P. But I don't know whether same homeomorphism works for either complementary components or not.
This is a little strange.
Yeah. But of course, this estimate is also there in the Schramm work where he's proving CKC theorem,
Yeah.
analog of this estimate.
Because their construction construct the homomorphism directly.
Yeah,
Maybe not highly depends on the complementary components.
I don't know.
Yeah, that's the.
But it's not my notation.
That's the smaller one. Are there any conclusions?